Hello, this is Bruce Wallenberg again. This is the second lecture on power system security. You remember that one of the things that we pointed out was that power system security or contingency analysis calculations are one of the largest computationally intensive tasks that are performed on the control system computers for power systems. So there's a real desire, a need to make these calculations run fast. And we're going to go through some of those strategies right now and show you the reasons. But just running brute force, thousands or tens of thousands of full AC power flows will never do, because it will take much too long to do that calculation. Many control centers these days stack up lots of computers and run them in parallel to gain speed. That's one way to do it, sort of building your own supercomputer. But these strategies here also are in use and have been used for a long time. So one of the ways to go fast is to simply study the system with approximate, with approximate but very fast algorithms, and that is historically has been one of the ways in which they've gained speed, and we're going to show what these approximate methods are, and they are still in use. Select only the important cases. Now this, especially initially, was looked on with a great deal of let's say technical suspicion by the engineers in the operations groups when we presented it to them, but gradually I think came around to seeing the fact that software can find the important cases most of the time. As I say, if the only alternative is just brute force, you're going to have to spend a lot of money for extra computers and so forth. So we talked about multiple processors, vector processors like the Cray supercomputers. There's now some work being done to use the NVIDIA processors, the so-called Tesla cards that you can put in PCs. When that gets to be more mature, maybe we'll see some of that coming into computer control centers. But large Cray computers, experimental, we were able to run thousands of power flows on Cray computers very fast, but those are huge computers and very expensive. They were never actually seriously adopted by the electric and utility industry. So then we just say use a combination of the above. Now, linear sensitivity analysis, very, very, very important, and we're going to go through the basics of it here. Perhaps another time we'll have a third lecture in this series to show how we do these, how we develop these factors. But the first factor is called the power transfer distribution factor, or PTDF. And the idea is that if I have a bus here, and I'm gonna put some power into the bus. So here's the generator output goes up, and this is bus I, and here is a load over here at bus J, and J is going to raise its load, and let's assume that we're in a lossless system here. These factors are done in a linear sensitivity, so there's no losses. But I transfer a megawatt from here to here. And someplace in the system is a line L. And I like to use this script L. And what we'd like to say is, well, if I transfer delta P, so here's the amount transferred, how much of that delta P ends up going through this line L? Now, it could be that it's almost all, or even 100% of it. It could be all the way down to 0 if this L is completely, well, decoupled. If, for example, this is a radial line, then none of it will go through. So it could be from 0 to 1. It could actually be from -1 to 0 to 1. Okay? So how much of a change on line L, delta, the delta flow on L, divided by delta P, that's this power transfer distribution factor. Okay? So obviously then, if I multiply delta P times the PTDF, I know what the delta F is. And this, the derivations are explained in Appendix B of that the chapter on power system security. So we use it like this. We say, well, the flow on L with the transfer is equal to the initial flow plus this PTDF times delta P. Now, the main use of this is to evaluate transactions. So if you're desiring to do a transaction on the power system, there are websites where you can go and you can say, I want to do a transfer from, and it can be for hundreds and hundreds of miles. If I want to do a transfer from Minneapolis to Chicago, let's say 500 megawatts from Minneapolis to Chicago, this thing will, the website software will then use the PTDFs to evaluate the effect of that 500 megawatts transfer on all of the transmission lines that are affected between Minneapolis and Chicago, and if that transfer causes any overloads, then it will come back and you won't be able to do the transfer. But it can tell you whether that's, it can also very easily tell you what the maximum transfer would be before some limit was reached. And then there's other negotiations you can get into, but it can do that very rapidly, and that's one of the uses of these factors. So you decide how much the transfer. That this would be the 500 megawatts here. This is pre-calculated for every line L. We have a base flow, and this is the resulting flow. And then you check this against the limit. The other type of linear sensitivity analysis is called line-outage distribution factors, or LODF. And the LODF is very, it's actually to my mind, it's a little simpler than the PTDF. So here I have a line K, and someplace else in the power system I have my line L again, and I'm concerned about an overload on this line here. And what what I'd like to know is this one has an initial flow on it, and suddenly the breaker's open on this line for any reason. If this line is lost, how much of this flow, which we call F0, and we'll put a sub K, how much of that flow, I'll put a dotted line, ends up flowing on this line over here, and then thereby increasing that line's flow. If it's the right sign, it could increase it, it could decrease it too, but if it increased it, would it send it, then you test it against its limit. So the LODF factor is the change in flow on line L over here, the change in flow on this line, divided by the initial flow on this line. And then to get this change in flow on FL, we just multiply this times the LODF factor. Again, this is derived. You've got to look at it and say, well, you know, if you want to know the effect of every line, every possible line outage K, and its effect on every possible remaining line L, then the LODF factors is actually a matrix that's the number of lines times the number of lines. Now the diagonal term is 0. It simply says how much flow is on line K after line K opens. The answer is 0. So we know that diagonal terms are trivial, but the rest of it isn't, and it's a fairly complex thing to calculate all of these, and a little bit time consuming. So with the testing is done, you say take the initial flow on K, multiply this factor, the L to K factor, add the result to flow L, and we have the so-called contingency flow, or the flow after the outage, and then we test that against the limit. Now, theoretically, I could run this for every line outage K and every line being monitored L. That's an awful lot, but it can be done, and it can be done reasonably fast. This is the way that control centers did their contingency analysis. I would say for the last 50 years, many of them use this method and still use it. Some of them. Okay, now a former student of mine. Here comes a little bragging from this professor. A former student of mine named Paul Barber was working with a group. And you can see a footnote in the textbook, but they came up with this term called a flow gate, and they instead of looking at the flow on a single line, what they wanted was a group. And you can see here they said, well, what we really want is what's the flow on a group of lines. So we say the flow gate is the sum of the flows on L1 and 2 and 3. It's the sum of the flows. So we put this circle around. We add up the flow. So this could be all the lines, let's say, coming from one company into another, or from one state into another. That's a flow gate, and it turns out that we can use these linear factors by just summing over all the lines in the flow gate. We can determine what the flow gate, how the flow gate is affected whenever you do a transfer or whenever you do a line outage. So I can treat the flow gates the same way I treat single monitored lines, and it makes more sense to treat these flow gates over large power areas because they will often act. I say act in parallel. If one line here increases due to a line outage, probably the others will too. And so if you sum it up and then say, well, what's the increase in the flow gate, and I can put limits on these flow gates too. Very useful concept, and one that you'll run into in many papers and documents. But many times flow gates are what people are more interested in than single line. Okay, we mentioned this earlier in the first lecture, voltage collapse. If I take a very simple circuit, here's a voltage over here of 1 per unit. I have a per unit X of 0.1 per unit on this transmission line. This is an AC system. Over here I have a voltage and a phase angle, and I have the real power P. I should also put Q here. Okay, I have a Q in this load, and I want to know what is the P and Q as a function of this voltage. Now this is fixed, and we'll say that theta at this end is simply equal to 0. This is the reference bus. And here's the two equations out here. You can solve it out this way as long as there's only an X in here. Put some R in here. you got yourself a very difficult thing to solve. You can only do it by numerics and so forth. In any event, this thing has a shape. So here is the power, and I'm saying that the power P just gets larger and larger. And let's say that the tangent just represents the amount of Q. Are we adding Q or are we subtracting Q? So it looks like the power factor. And here's the one where the Q is basically the power factor is just going up unity. It's not drawing any, and you can see that the voltage starts out, and it starts out at 1 at V, but as I draw more and more and more power, the voltage gets lower and lower. About here is where 0.9, your system is in trouble. If you go much further, we reach this point right here, and any more power, there is no solution. There is no solution. There is no voltage magnitude at this end that will support any more P. Now, if we have a Q where we're adding Q into the system, then this line goes up, like this one out here. It goes up, and then it comes down, but it still comes down here. But I can get more real power through the system. But eventually, I still reach this thing. This thing has been called a nose curve. Okay. If all of us can see why that curve is called the nose curve, and when it reaches the end of the nose curve, there's no more solution. And generally, what we say is that when you get more power drawn through this thing, you are beyond the point of the nose curve, and the system, the power system, goes into voltage collapse. All the voltages begin to drop all over the system, and the system will literally shut down. And voltage collapse, the large power outage in 2003 in the United States, beginning in Michigan and then along the southern shore of Lake Erie in Ohio, was a voltage collapse. The causes of it we could talk about endlessly, but the initial effect on the system was a voltage collapse. Now here's one of the things that's very, very important. If we have, let's say, pre-disturbance, we have a system, and let's say it's operating right here with this much power. Here's P. Okay, so 340 or 330 megawatts, and then suddenly we remove one line. What happens is, if we take these curves that we had on the other page and we reduce, we increase this. So suppose this actually had 2 circuits, and now I took one of the circuits out and it went from point 1 to point 2, then these curves drop back like this. They collapse back this way. Well, that's what we're showing here, is that the post contingency, where you have less transmission lines in parallel, therefore you have more impedance, you have a curve that doesn't extend out as far. And what it says is you really have to check for voltage collapse under the disturbance condition, because if you remove the transmission line and you were operating here, and now you're way beyond this nose curve, this point right here, you're going to hit voltage collapse, and you won't be able to do anything. Once it starts to go, it's a phenomenon that it doesn't happen instantly, but it happens almost without the ability to intervene. So we need to do AC power analysis on modern systems, and I said this is the so-called brute force here. List of possible outages. Pick an outage from the list, run an AC power flow, test for overloads. Here, if there's alarms, we stick an alarm out and it would go on some screen. Here's a screen in the control center. We get a message and we get this sound coming out. I'll draw, let's see if I can draw a little bell. There's a bell sounding, it's really electronic gong going off. The operator has to realize that the contingency analysis says that particular outage, if it goes, you're going to have overloads or voltage problems, and you do it for all the lines. And this takes a long time. So, if we took the full list and we selected the bad cases, now we're going to show how that's done in a minute. So we had a much shorter list, and then we did the same loop, but we're selecting from a shorter list, then we could get the thing done. I mean, maybe we take tens of thousands and we get these down to a few hundred. And it turns out that if you build a power system and you design it right, under even the most heavily loaded conditions, out of tens of thousands of lines, there's only a few hundred that are going to cause problems. If you have a system where tens of thousands of lines and thousands or several thousand of those outages are going to cause problems, you probably haven't designed the system well enough, and or you're operating way beyond what the design points for that system were. You're transferring too much power, or that the load is much too high. And you probably need to if that's the condition you're in, you need to add transmission to bring that situation under control. Now, contingency selection. This is the process. This is this process up here. Select the bad cases. We use something called a performance index, or a PI. Here's the words over here. Performance index. And this is something that you need to understand. It's a mathematical concept, and I'm smiling here because other people used to. There was one engineer one time said that all the secrets are held inside this PI. In other words, that there was something magic about it. There's nothing magic about it, but let's explain here. You take and you sum over all the lines that you're monitoring, and you monitor the flow on line L divided by its maximum to some 2n. And so I say this is 2n, and this is PI flow. There's an n here. Now, this simply says that let's suppose that this was just that NP n was 1. So then this was squared. Well, if the flow is less than P max here, then this will be less than 1, and when I square it, a number that's less than 1, when you square it, it gets even more less than 1. If it's greater than 1, let's say it's overloaded by 50%, if it's 1.5, and then I square that, then it gets to be larger. Well, it works even better if I take n equal, let's say 3 or 4 or 5. So 2 to the times 5, this to the 10th power. Well, that's kind of large. Let's say to the 4th or the 6th power. When you do that, any amount that you're over the max, this explodes. It gets to be very large. Any amount that you're below the max, if it's a number less than 1, then you raise it to the 4th or 6th power, it gets to be very small. And you sum this number over all the branches. So if PI is large, it says that someplace in there I have an overload. That's all it is. It's a single number. But it gives me a measure of whether I have any overload on the power system. If all of them are below their limit, then the PI will be be a smaller number, a much, much smaller number. Now, one of the problems, of course, is that if you get near enough to 1 and you sum over a lot of lines, well, then this gets to be a value. And you have to evaluate it out of practice and to see when you get a few overloads, this number will get to be large. It'll go up by a large factor. You can also do this kind of thing. This is the same one that we just did here. You can also do it for a voltage that goes below its min or above its max. And these are the formulas here. We're concerned with the min, that it go below that, and of course then we have to put the min on top, and then if this gets below the min, then this explodes. If it goes above its max, it's going to do the opposite, so we have to we invert the fraction here. And again, these are summed over buses. So this is a PI that covers both flows and voltages in here. So how do you use this? Well, we run what's called a friend of mine at when we were working on this method. A friend of mine invented the term 1P 1Q, and it's very simple. You're going to run the decoupled power flow. So we build our B prime, B double prime matrices. We do 1 P theta calculation. We update the thetas, and we do 1 PQ. So the 1P up here refers to 1 P theta calculation of the decoupled power flow, and then a 1Q is 1 QV calculation. We update those. We're all done. Now we take and we calculate the PI. Here's my PI, this formula that I had on the previous page here, and I calculate the PI and I store it. This is the best thing about it, is that I store it, and then I do the next outage case, and I do 1P 1Q, store the PI, 1P 1Q, and so I have one outage for each entry. Now what I want to do now is remember, if PI is large, I would like to study that case first. And so I'm now going to take this, and I'm just going to do a sort. And we sort with, and we get the largest numbers at the top and the smaller numbers at the bottom. And then, pardon me, I'll come back to that in a minute. So then I say, well, I'm going to take the largest ones at the top. I could either make the cutoff here based on the value of PI, or I could simply say, well, I have, let's say, 5,000 lines, and I'm going to study 200 of them. So here's the very largest, and here's the 200 entry. Or as I say, you could adapt it and say, well, once I've got them sorted, it turns out that after I get beyond the first 120, they're so small that there's no more overload, so I can stop. But in any event, then I run full, okay, full AC, right? Full AC power flow. So I run full AC power flow as I come down this list. And that way works. That works very, very well. And how do we know? Well, we can go back and we can compare it. There's an example in the book where we compare it to the brute force, where I solve every single AC power flow, and then I can compare it to this method, and I can say, okay, did I catch the bad cases? And generally, yes, it will. It'll catch the bad cases. There is no great value in letting the computers grind out AC power flows on hundreds or thousands of cases that don't amount to much, don't have any overloads. All right, here's another another way of doing this called concentric relaxation, sometimes called bounding, and another method called adaptive localization. All of these are methods that have been applied, and I would say the adaptive localization is one of the best, and it has achieved very, very, very good results. Concentric relaxation says here's the line that we're going to take out. So layer 0 includes just the buses at the end of the line. So that's this bus and this bus. And then we go out one more layer. And we add only the buses that immediately connect to the buses at the end. And we say, let everything else be fixed, run a power flow here based on the fact that this line went out. Here's the circuit breakers went out. And if I get a lot of movement out here, I get a lot of change on these lines after that power flow, well, go out and do the next layer and keep it expanding outward like that until you get enough of the system in there and you run this outage case and it doesn't affect the rest of the system that much. Now that's a interesting concept, and it is true. A line outage does not affect the entire power system. I used to say to people, does a line outage in the state of Maine affect a lot of flows down in Louisiana or out in Minnesota? And the answer is no. It won't affect it that much. This is not true for generator outages. They can be felt a lot further, but line outages, no, the effect is diminished further and further away from the line, the changes in the flows. And this basically captures only the part of the system that is affected. Bounding is a similar technique. It's a little bit more mathematical technique to find, again, the significant layers of the system that are affected. So they're very similar to each other. Adaptive localization is a technique that achieves similar results, but it runs the Newton power flow, and during the power flow it says if you start out with just the two lines here, and it says if there's an effect on other buses, well, then we start including them in the Newton power flow. And so you'll see it start to do the Newton power flow on 2 buses, and then maybe 8 or 10 buses, and it keeps running the Newton power flow. And so there's an expansion as it solves from the first 2 buses out to 20, 30, or 100 buses, and then as it begins to converge, once a bus has converged and is not being affected anymore, as the other buses are converging, we drop it back out. And so it's adaptive in that it starts dropping buses, and at the very end of the calculation there may only be 1 or 2 buses again that are being adjusted. And so it first expands out, picks up all the change, and then as the changes start to dampen out, and if you want to put it that way, and that method can do complete AC power flows of contingencies, and it can do them very rapidly. Remember, it has a solved case, and so it does the solution very fast because it's only doing it on a small fraction of the system, and it can solve those outage cases very, very fast. And it takes a lot of very sophisticated programming, very sophisticated sparse matrix techniques, but these have been developed and are being fielded with software today. Thank you very much.